So as promised, I'm going to upsolve this question that I didn't get in contest. I'm actually kind of mad at myself because I definitely have seen this type of problem before. But it's kind of cool because I'm going to make a video. All three of these problems, are the exact same question. Like no, like they're just genuinely like I'm not even like they're genuinely the same exact problem. I mean, of course, there's like nuances and like they're not like they're obviously nuances, but like literally, if you solve this problem, you know this idea, and they all use the same exact idea. And you by the title, you're probably like saying intermediate value theorem in competitive programming, the competitive programming intermediate value theorem. Um, I guess. And this is a really exciting because you can see like I guess this proves that like if you do enough problems, you start to see similar ideas. Um, and the whole idea here is if you have a function in which it goes up by ones and negative ones, then we can say that function is continuous for all integers. And I'll explain more. So again, I'm not going to explain all these problems. I'll put all these problems in the link in the description, and you guys can read it. This is definitely the most. Let me. Okay, this one's obviously easy to understand. This one, uh, bracket coloring, and these ones might be annoying to understand. So try to read them carefully. And I will explain, I guess, this question. But it really is just a bunch of details. The general idea that you can get is the most important when you're like learning a problem because no one's going to remember the nuances in a problem, obviously. So the idea here is if you have like just in general, like if you have like so in general, we'll start with like what is the intermediate value theorem, anyways. I'm not obviously this is competitive programming, so I'm not going to prove this. In fact, it's actually very difficult to prove the intermediate value theorem. You might be saying, what, isn't it extremely obvious? Like and yeah, it's extremely intuitive. The intermediate value theorem is extremely intuitive. That I don't think that someone needs to have like a rigorous proof to be completely satisfied, unless you're like some perfectionist. But this is basically what the intermediate value theorem is saying. It's saying we have A. It's saying we have maybe some B here. We like cut some function here. If the function is continuous from A to B, and what we define continuous continuous is like the limit as x approaches that place is equal to f of x, and there's you can worry about basically like for competitive programming. I mean, and most of you are probably like really good at math, anyways. Um, um, Basically, continuous continuity is just saying a dumb way to define it is just saying I guess sort of can you draw the function without picking up your pencil? It's not a dumb way to find. This is actually exactly like that basically gets the job done. Can you draw the function without picking up your pencil? That's sort of the non-rigorous way to define continuity. So you can clearly see that from A to B, this is continuous. But in general, when we say continuous, right, it's always assumed when we say a function is continuous, we never say that it's continuous for all real numbers, right? But like, I I mean, if you get really rigorous, right? But usually, most people just say, okay, this function is continuous. It's continuous. It's continuous. Continuity doesn't have to just extend to all real numbers. We can extend it to all integers. We can extend it to all multiples of two. We can extend it to all zero point 0.5 increments. You can generalize the definition of what continuity means. And that's exactly what these questions are doing. They're extending continuity for integers because in competitive programming, we're never worrying about real numbers. Usually, most like 95% of the problems, at least what have I've seen, and I've done like quite a bit of problems in competitive programming. I'm not saying I'm good at it, but like I've done obviously problems. What I've seen is that most of them deal with integers, right? Like you're not going to usually they don't give you like an array of like zero point 0.5 and zero point 0.2 values. That like rarely happens, right? And so the idea here is that you like in these problems, they basically give you in these problems. What's happening is they give you like it's basically just a string of ones, negative ones, ones, negative ones, negative ones, negative ones, negative ones. And this is you can think of this as sort of like you can think of this as a function. So we're gonna use the intermediate value theorem here to actually like, just and once you know these, it really trivializes all these problems. Like it straight up just makes all these problems trivial. But this is a very very subtle thing to notice though, which makes these problems like difficult. But once you know this, it's very easy to do these problems. Um, and I stress this because basically, if you were to plot this function, you go up by one, down by one. In fact, I'm going to make this shorter. Go up by one, down by one, up by one, up by one, up by one. We're going up by one 3 times. Down by one, up by one, down by one, up by one. And I sort of want to go like down like 5 times. That's okay with y'all. Um, yeah, just to make this more interesting. So the graph will look something like this. So if you were to plot this function, in fact, I'm going to now sort of plot the functions. These are like sort of the points. This is like sort of the rough points, I guess. So like these are like where the ones and the negative ones are. Like you increment by one, then you go down, whatever, right? So here's what's really interesting about this. We can say this function is continuous for all integers. It's not continuous for all real numbers. You could, in fact, if you're only adding ones and negative ones, you can only achieve integer values. But think about it like intuitively, right? Clearly, you can see that like if you do this function, it's continuous for all integer values, right? All integer values. Think about it like this, right? If I cut this interval where the max occurs, and I cut this interval to where the min occurs, right? This occurs here. There's multiple maxes. I guess I should have drawn like a distinct. I should have drawn like where the max is like. There's only like the max only occurs in one place. I guess I should have done that, but it's fine. If you like just cut where the min occurs, so this is where the max occurs and this is where the min occurs. I claim you can achieve every value in between min and max, and this is just the intermediate value theorem. Isn't it? This is just an extension of the intermediate value theorem. This is literally just an extension of the intermediate value theorem. Which is very, very extremely intuitive. So you don't need to do a proof to satisfy that. Unless you're a perfectionist, then go for it, man. But it's satisfying to me because it's very obvious. Since you know that since you know that it's continuous, since you're moving, just think about it for real numbers, right? Like for integers are spaced out by ones. So you transitioned from an integer by ones and also by negative ones. And so that's sort of like the basis of how you transition between integers. And therefore, you notice that you can now claim that this function is continuous for all integers between the max and the min. Like if you cut, so the idea is that you cut the interval where the max occurs and you cut the interval where the min occurs, then you can achieve every value between min and max. And this is just like this should just be obvious now that like if you were to plot this, you could easily see that it's continuous, um, because you're using what you transition between integers from only by ones and negative ones. So that's like literally just definition, right? That's how think about it. An integer like can be represented by ones and negative ones, right? And so this is like just you can just see it's continuous. And so the idea is that you cut. This idea should be very intuitive now. You cut where the max occurs, and you cut where the min occurs, and then you could say you can achieve every single value in that range. And this can also prove why Condain's algorithm with this similar like and this sort of thinking of like turning things into ones and negative ones, like you can also prove like a lot of things like maybe Condain's algorithm with ones and negative ones. If you can search it up, if it's just maximum subarray sum. If you had ones and negative ones, you can prove a lot. You can like this is a really useful way to think about ones and negative ones like on a graph. Like it solves this problem, it solves that problem, and it solves this problem if you think about it like this. And that's how I was able to solve this question. I actually did the contest, but I left early, troll. And also like didn't really care. I don't care too much. Um, but yeah, so like you notice that this is just continuous for all. I think you get the point. And that's pretty much it. Like in this question, you have the same thing. You have ones and negative ones, and the idea is that you're trying to see if a value k, a subsegment, sums up to k. Same idea. If you know where the max occurs and you know where the min occurs, cut the interval there, and you can achieve every value in that range. And then you say, is k in that range? And to keep track of the maximum and minimum, there's a couple of details there. But the point is, this video is not really to care about those details, because it you there's actually a couple ways to do this. You can actually build the tree and then just like save the queries, and then you can do Condain's algorithm on a path of a tree. Condain's algorithm is just like saying, okay, if you want to maximize it, keep adding it and maximizing, and once it goes to zero, then start a new sum. That's also Condain. You can actually build a tree and do that. Otherwise, you can use like really, 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 really basic DP, and it's a really basic DPCC. It's really, really basic. But yeah, you can do that. You can sort of think about that yourself if you want to. I mean, this is really not the idea that you're sort of pulling, and you could pretty much Google this if you needed to. But that's really this problem, and then this problem is the same thing. I haven't done this problem. I did this problem a year ago, so I don't remember it. Um, but I'm pretty sure it uses the intermediate value theorem. Um, yeah, so it says it's basically saying that you can transition by negative 2, 0, or 2. Therefore, like you can generalize this, right? Basically, if you have k's and negative k's, the function is continuous for every multiple of k. Think about it, it's very easy because think about it, you could just divide everything by k. This should be obvious, right? You can generalize this. So you have k's and negative k's. The function is continuous for all integers, all integer multiples of k. So that's also very obvious too. And you can also do this question too. I also recommend doing this question too. And then also bracket coloring. This is very interesting because what you can do is you can think of you can think of the right opening brackets as ones and the left opening brackets as negative ones, and you can like plot it on this function. And once you do it, it immediately solves this question. Like it's almost like boom. Like you get the idea in like 1 minute. Once you do this, and I got penalties, pool. But yeah, once you sort of think of it like that, then you solve these questions there. But yeah, that's really just cool thing. I think that's the coolest thing ever. Though, it's really just these are all the same problems. Once you realize that you have this general idea, and this is really good. This is how you extract the richness behind problems. You sort of think about how you could generally apply ideas between other problems, and I guess yeah, this idea is more subtle because it doesn't actually give you ones and negative ones. You convert them to ones and negative ones, and then yeah. So yeah, that's it.